Welcome to my presentation, Visualizing Differential Expression Data with FlowSets. My name is Felix Offensberger and I'm from the Bioinformatics department at the LMU Munich. More and more multi-omic, large and differential expression datasets are available, like here on the right side, TCGA with a subset of 17 cancer types. Scattered analysis or pairwise comparisons make it difficult to interpret results and make it challenging to identify and understand underlying processes. Differential analysis of large-scale expression datasets are crucial to derive disease pathways and condition-specific causes. Here at our cancer dataset, we are interested in the change of cancer and corresponding healthy tissue for all the 17 different cancer types. Large-scale comparisons, like within or between cancer types with traditional methods, would be difficult. Newly developed methods for complex scenarios are needed. Here we want to gain overview over many conditions and a flexible analysis of multi-differential datasets. Here we introduce FlowSets. FlowSets make it easy to get an overview over many conditions. Here on the x-axis. With FlowSets, many types of data can be represented, and therefore also different types of conditions. Here called more technically states. Within each condition, features, for instance genes, can have different expression levels, which are categorized in classes. Classes can represent expression values, fold changes, or any other type of input, which is before categorized. FlowSets visualizes the change of features between those states. These changes can be interesting in various scenarios. As multi-dimensional data, where same technique is measured in many different conditions. Multi-ohm data, where we have different type of signals, for example, ATAC-seq peaks and gene expression. Time series, where we have a recurrent pattern over the time, or many more, like marker genes, clustering, drug screenings. Here, since we want to categorize continuous expression values, one either has the choice to find the threshold for binding the continuous variable or to retain its continuous character by placing the gene at certain fractions into a bind category. Because finding reliable thresholds is problematic, and experimentally measured data also exert some degree of noise, we opted for representing genes in multiple categories using the well-studied concept of fuzzy theory. This way, we avoid the problem of thresholding pretty much and are able to represent rather inexact measurements in an easily understandable way. We take our input, in this case fold changes, and fuzzify it through a given user-given fuzzy concept. Here, for fold changes, we normally have the linguistic classes downregulated genes, neutral regulated, or upregulated genes. For a fold change of 0.6, we would say that it's slightly upregulated, so we assign it with 0.6 to the upregulated category and 0.4 to the neutral. Normally, a fold change of 0.6 is not downregulated at all, so the membership here is 0. We now show the transition of fuzzy values as flows. For a given feature, each node holds the membership of the feature at given state and class. As our example on the fuzzification, a fold change of 0.6 is with 0.6 in the upregulated class and 0.4 in the neutral class. In the next state, the feature is with 0.9 in the upregulated class and 0.1 in the neutral class. The weight for the transition of the up class in the first state and the up class in the second state gets now a weight of 0.6 times 0.9. To get the weight for one transition between two neighboring classes, we use the dot product. We connected our example fold changes from falsification with an even higher. In the next state, the gene is fully in the upregulated class and afterwards neutral. Combining all features and states in FlowSets, we get an overview over the whole regulation in the data. The biggest mass is in the neutral class over all states. We have edges where we know the membership of each feature, and we can also track a feature over the whole flow set. After building our flow set, we can now perform different types of analysis. One can be interested in features on the left side in the feature-centric analysis, where we select single or multiple features and are interested how does a gene or gene set flow through the flow set system, or how do genes in a gene set cluster for a given classification. On the right side, we are more interested in the flow-centric analysis. Here we can have a selection of nodes or edges and inspect which genes follow a specific pattern. What is the membership distribution within a flow? And what is the functional meaning of a flow? So which gene sets are contained? Looking now at a more complicated example where we have 16 states and 5 classes of differential expression, one can now look at the membership matrix of a gene set on the left, which is still difficult to understand the pattern of regulation of genes in the matrix. FlowSets can now visualize a single gene, here in blue. For the selected feature, a strong rhythmic pattern is seen, which is downregulated in 2 states and then upregulated in the next 2. This differential regulation is not as strong in the end states. And we can also visualize a complete gene set, looking at the behavior of all the genes within. Here we can perfectly see the different behaviors of the 3 annotated clusters. The orange one is upregulated over all states. The gray one is conditionally upregulated or neutral based on the condition, and the blue ones are showing a completely different pattern. In the feature-centric analysis, we found no interesting regulational pattern over our flow set of single or multiple features. In the flow-centric analysis, we are now interested which features have the similar pattern as genes we observed now. These patterns can be fairly different. We can have oscillating pattern, as described before. In multi-omics, for instance here in ATAC-seq, we can have an open chromatin region which is linked to an open promoter and the expression of a gene. We can have circadian rhythms which are recurrent for each day, but also other specific ones like marker genes, V-shaped patterns, or dysregulated conditions. In the flow-centric analysis, we can now ask the flow set questions like which genes are never downregulated. Here we choose nodes and edges which are never going through the downregulated classes. The simplest form would be in single path. Here we have multiple. We are now interested which features belong to a given pattern. To calculate the membership of each feature to the given pattern, we are now looking at the restricted flow set. We are interested how much membership can flow from the green sources to the red sinks. On left, we are comparing the full flow set, with right, the restricted flow set. We initialize both sources with the memberships in the source classes. Normally, we would have all edges and all edge weights Wx x times Wy, and in our restricted case, we only have the selected or restricted edges. Using a belief propagation approach, also known as sum product message passing, we recalculate all subsequent node memberships in the restricted network. Iteratively, each transition can be updated, using dynamic programming for efficient implementation. Finally, we get the membership of all features in the restricted network if we sum up the feature memberships in all sync nodes. In the full flow set on the left, all features have a membership of 1. On the right side, we have genes which are not belonging to our pattern. On the left, with a membership of 0. They had been downregulated at any state. And on the right, genes which are never downregulated in our system, so the whole membership flow in the restricted flow set. This membership can then be used for further downstream analysis, such as gene set overrepresentation analysis. Analyzing now the TCGA data from the beginning, calculating fold changes between cancer and healthy tissue of every cancer type, divided into 5 fuzzy values we can now input into FlowSets. Using FlowSets, we identified SIGDEC8 as the only gene which is positively associated with kidney cancer. While this finding has already been reported in literature, it is easily checkable with our FlowSet tool. Additionally, we can check if there's any regulation besides the 3 kidney cancer types, as seen here in the third state, slightly downregulation. Likewise, EGFL6 was already described as a pan-cancer gene, which is made easily understandable using FlowSets. Similarly, we could ask whether there are genes which are primarily expressed in lung cancer. Indeed, such genes exist, like for instance FOXI3, which has already been shown to be involved in metastasis formation. For a gene set overrepresentation performed on the selected FlowSet pattern, we learned that lung cancer is associated with several immune processes. Interestingly, also the IL-22-mediated signaling pathway, which is known to be elevated in lung cancers. These examples show that using FlowSet, it becomes easy to visualize and interpret large-scale data sets, even when comparing different gene expression results. The falsification of the input data makes expression levels on the one hand more understandable, but also enables the partial representation of genes or features in these expression classes, and therefore a more detailed analysis. We would like to thank the BioVis COSI and the ISMB ECCB 2023 to present our tool FlowSets, and invite you to visit our poster B59. We are looking forward to welcome you there. Thank you for your attention.